This is topic 9.8, cell potential and free energy. Today's objective, explain whether an electrochemical cell is thermodynamically favored based on its standard cell potential and the constituent half reactions within the cell. So again, we're looking a little bit at electrochemistry. A couple of terms that we should know: cells, voltage, standard cell potential, oxidation, reduction. We're going to look at Gibbs free energy, and we also have an equation you're going to have to know how to use correctly, hopefully. As we saw recently, chemical reactions can be used to generate electrical energy. By comparing standard reduction potential values in volts for half reactions, we can then calculate the standard reduction potential for the cell overall. This will tell us if something is a galvanic or voltaic cell because it is thermodynamically favorable. If it's unfavorable, it's called an electrolytic cell. Those require input of electrical energy for it to proceed. Okay, so you need to be something you need to be aware of. This comes usually from a battery or a power supply, and if you vaguely remember physics, this is how you demonstrate. Hey, what color is that? Oh, wow, my bad. If you vaguely remember physics, this is what it looks like. Interesting. Okay. To calculate the value for a cell, we need to look at a table of standard reduction potentials. Those you'll be provided so you can, like I said, the resources are there. It's how you apply them that it will determine whether or not you're successful. My bad. Okay. The cell potential is calculated by taking the sum of the voltage for the reduction reaction, the best reduction reaction, and the voltage for the oxidation reaction. You should remember that when you flip it, the reaction, you have to change the sign. But if you have to multiply by like 2 or 3 to cancel out the number of electrons, you do not do that to the voltage. Since the voltage can be used to predict thermodynamic favorability, it is proportional to Gibbs free energy. We can use the E0, the voltage, to calculate Gibbs free energy through the formula delta G0 equals negative N times F times E0. N is the number of moles of electrons that are transferred. I don't know why it's showing up like this. Interesting. F is called Faraday's constant, and it is 96,485 coulombs per mole of electron. This constant comes from the charge of an electron multiplied by Avogadro's number. E0 is the voltage. However, for the units to cancel, you need to know that 1 volt equals 1 joule per coulomb. Gibbs free energy is typically given in kilojoules, so you need to convert your joules to kilojoules. Calculate the value of delta G0 for the reaction that is provided here. We have Au3 plus aqueous produces 3 Ag solid, producing gold solid plus 3 Ag plus. The E0 is given positive 0.70 volts. So delta G0 equals negative N F E0. I'm going to erase that. Okay, I guess I won't erase that. Cool. So recognize your variables. N equals the number of moles of electrons that are transferred, which you see, you saw it before when we did the reaction before. Also, you see the 3 plus and then the 0 here and the 0 and the, so 3, 1 plus. So 3 electrons are being transferred. Your F is Faraday's constant, 96,485 coulombs per mole electron. Your E0 is 0.70 volts. So delta G0 equals negative 3 moles of electrons times Faraday's constant, 96,485 coulombs per mole electron times 0.70 volts. However, let's see. How does it go? 1 joule is 1 volt times 1 coulomb, which is how we're going to cancel out our units. And then it doesn't really tell you what it wants it in, but we'll keep it in joules and we'll convert to kilojoules afterwards, so that's fine. In the calculator, I end up with negative 2.0 times 10. Oh, wow. I don't know what's going on there. Negative 2.0 times 10 to the 5 joules, or negative 2.0 times 10 to the 2 kilojoules. So if it doesn't tell you, you can leave it in joules, but if they do tell you, you need to convert it to kilojoules. So read this, pause the video, and then try it out yourself and see what we get. Given the following standard reduction potentials, write the overall thermodynamic reaction that would occur, calculate the value of E0, how many moles of electrons are transferred, calculate the value of delta G0 in kilojoules. So we look at our reactions, we see that this is the higher number for the reduction potential, so this is going to be reduced, the other one will be oxidized. If the one that's being reduced, you can keep it the way it is, the oxidized you need to flip. And we can see that in both of them we have 2 electrons that are going to be transferred, hint hint. So we're good to go with this. So I'm going to flip this one. Overall thermodynamically favorable reaction, chlorine gas plus H2S gas produces 2 chloride ions in aqueous solution plus S solid plus 2H plus aqueous. Calculate the value of E0 in volts. So I'm just going to add these, but remember if I flip this, I need to make that the opposite. So 1.36 volts plus a negative 0.12 volts will produce positive 1.24 volts. How many volts of electrons are transferred? It's a 2, so 2 moles of electrons. If you want, it's best that you put units with everything. If it's a number in a unit, like how many moles of electrons? 2 moles of electrons for your answer. Just be thorough. Just be, just so you know. Calculate the value for delta G0 in kilojoules. So remember that delta G0 equals negative N times Faraday's constant E0. Okay. So we have how many moles? We have 2 moles, which we kind of introduced here, so we can say that this, let's see, N equals 2 moles of electrons. Times Faraday's constant, which you're kind of given, 96,485 coulombs per mole. You have your E0 right here. This is your N times 1.24 volts times 1 joule per 1 volt times 1 coulomb. And since I want this in kilojoules, I want to just say that in 1,000 joules, there is 1 kilojoule. Okay, I regret I'm going to change this to a different color. I do my math, I end up with negative 239 kilojoules. So don't use your sig figs. Do not base it off the number of moles. That's just from your, it's like a coefficient in a reaction, right? So you don't want to base you never base your sig figs off of that. And this is a constant, a value, so you don't base your sig figs off of that. Here, the number that we got in the problem, the answer we do our math, we're going to base our sig figs off of that. So if you have any questions, please let me know. Thanks, guys.